cascade of unresolved data falls into place. On August 4th, a preprint described how TESS, our exoplanet hunter, quietly recorded 3IATLAS months before discovery. After careful stacking and point spread function analysis, the signal behaved like a tight, unresolved beacon with no discernible halo in the TESS band. It brightened steadily, but stayed compact, as if it were just another star traced across the detector. Weeks later, infrared spectroscopy spoke a different language. JWST reported a gas coma enriched in carbon dioxide over water by roughly 8:1, among the highest ratios ever measured for any comet, detected when the object was still more than 3 astronomical units from the Sun. Molecules glowed in the dark while the optical images suggested restraint. The calendar adds pressure. Perihelion falls on October 29th, a natural experiment only days away, when sunlight will push temperature and stress toward their limits. Meanwhile, articles and briefings multiply, each sketching a different portrait of the same visitor and hinting at an object that will not fit inside our familiar categories. Here's the puzzle. One sensor reads a stubborn point, another sees a roaring atmosphere. Both are reputable, both are careful, both insist they are right. When reputable instruments disagree, the cosmos is usually asking a better question than the one we started with. Here on this channel, we slow the heartbeat without slowing the mind. We take the most persistent anomalies and treat them with patient curiosity. We follow the evidence, keep the speculation grounded, and let wonder do its quiet work while you drift toward rest. So, before our journey begins, take a moment to like the video and subscribe, but only if you feel a genuine connection to the mysteries we explore here. And please, let us know your location and the time where you are. These small markers on the map make our quiet community feel closer, even across oceans and deserts. Now, dim the lights. Let the world outside fade away, and let's drift into the cosmos together. 5 days before closest approach, the sun sharpens every edge. Behind city windows and winter clouds, an interstellar fragment slides inward, quiet as frost, carrying a chemistry that argues with itself. In optical light, TESS treats 3IATLAS like a disciplined point. That is what TESS does well. Its cameras are built to watch stars for small, steady dips. With a broad bandpass and a generous pixel scale, it cannot paint delicate structures, but it can tell when a source spreads. Here, the co-added frames and careful photometry yield a compact profile that behaves like a star pulled along a known ephemeris. There is no obvious skirt of dust, no soft extension that would betray a wide optical coma. In the language of the detector, the object is neat. Infrared is a different dialect. JWST listens for vibration and rotation in molecules, the signatures of gas uncurling in space. In that spectrum, 3IATLAS is anything but quiet. Carbon dioxide dominates over water near 8:1, a number that sits far from the median of our comet catalog. Water shows up too, traced by daughter products and by ultraviolet detections from other observatories. But the balance is strange. If you were to put the chemistry on a scale, the platter-labeled carbon dioxide falls with a decisive thud, while the water side rises. The outgassing is real. The coma is there. It just glows in wavelengths that optical stacks barely feel. Picture it. A hard glint crossing TESS's field like a pinhead of cold light, while beyond the visible band, a ghostly sphere of gas blooms and thins, transparent to one instrument and emphatic to another. The object is both crisp and diffuse, both restrained and unruly, depending on which senses we bring to it. Two hard facts cluster easily. Perihelion is set for October 29th, a fixed point when solar heating should intensify whatever physics is already in motion. The designation is official now. See 2025 N1. the third interstellar visitor confirmed by modern surveys, discovered on July 1st by the ATLAS project. These are not rumors, they are anchors. The grounded speculation follows from the instruments. TESS's wide pixels and optical band reward compactness. JWST's sensitivity favors molecules and thermal glow. If dust grains are unusually scarce or small, if gas is richer in carbon dioxide that does not reflect sunlight well, then the visible coma could be faint even as the infrared coma is strong. Under that scenario, the datasets do not disagree so much as they speak past each other, each honest, each incomplete. Yet the ratio nags. Most comets carry water as the familiar workhorse, with carbon dioxide as a strong partner, but rarely this dominant. An 8-to-1 tilt hints at deep cold, at ices preserved in a nursery unlike our own, or at internal plumbing that exposes carbon dioxide vents while water stays trapped a little longer. It suggests a crust that fractures along unfamiliar seams, releasing volatiles in layers rather than in a blended breath. Vivid image settles the mind again. Imagine a snowfield sealed under volcanic glass, cracks open in long, straight lines. From those lines, cold vapor flows without sparkle, almost invisible in daylight, plainly seen only when night vision goggles translate wavelengths into green. The field looks empty until the right sensor hums. For a compact technical breath, gather the numbers. Perihelion, October 29th. Discovery date, July 1st. Distance during JWST's spectroscopy, a little over 3 astronomical units. Carbon dioxide to water near 8. Each figure is a handle you can hold, while the rest of the picture shifts. So the open question arrives, not as a threat, but as an invitation. If one object can be star-like to one instrument and comet-like to another, what else hides in the gaps between our senses? Is 3IATLAS teaching us that coma and core can decouple more cleanly than we expected? Or that our categories for interstellar ice are still too narrow? For tonight, there is comfort in the method. We will keep the chemistry grounded, the imagery gentle, and the suspense contained inside real dates and real measurements. The paradox is not a cliff, it is a staircase, and we have already found the first few steps. Within the red hush of TESS, 3IATLAS refuses to blur. Hours compress into one precise point, like a pin pressed through the sky's fabric, resisting every reason to smear. TESS was built to watch stars breathe. Its cameras hold a wide slice of sky, patient and even, so they can measure tiny brightenings and dimmings that betray a planet in transit. The instrument is not a painter of fine filaments. It is a metronome that feels for steadiness. When it looks at a comet, the first test is simple. Does the light spread beyond the shape of a star, or does it hold tight? On the detectors, the visitor behaves like a disciplined star that happens to move. Analysts take thousands of frames and shift them along the object's predicted path, so the interstellar point stops drifting. Then they add the frames together with careful housekeeping for background glow and cosmic hits. The stack grows deep. The stars slide into streaks. The moving target stands still. If there were a low surface brightness halo large enough to matter, the final profile would swell. It does not. The core is compact. The shape looks like the instrument's own fingerprint. Picture the result. A single salt grain on black velvet riding a slow conveyor belt. Everything else becomes a blur, but the grain stays sharp. If dust were flying off in a bright skirt, the edges would soften. They do not. The point holds. 2 hard facts anchor the calm. TESS works in a broad red band that reaches from about 600 to 1000 nanometers, where reflected sunlight reads as a clean continuum, and the instrument feels modest thermal glow. The pixel scale is about 21 arcseconds, which means that large and faint coma can hide below the threshold if their light is too spread out. The comet, if it is a comet at all, invisible light must either be unusually dust poor or be shedding particles so fine and dark that they vanish into the background. Within the instrument's language, point-like means point-like. The team checks for asymmetry with the usual rituals. Rotate the field to test for scattered light from the spacecraft environment. Compare the point spread function of nearby stars with the target. Fit a model that allows for wings wider than usual, and ask the data whether it prefers them. The answers come back dry. TESS is seeing something compact. It is not an illusion born of a noisy corner or an unlucky background patch. Gather the compact numbers in one breath. Pixel scale near 21 arcseconds. Red band from roughly 600 to 1000 nanometers. Full frame images stacked by the thousands. Exposures grouped across many nights. Background sampled from 4 directions. All of it tuned to one narrow question. Does the light hold its shape? A grounded speculation follows. If the gas around 3IATLAS is dominated by molecules that radiate strongly in the infrared, then the optical signature can remain faint even when the total outgassing is robust. Carbon dioxide does not scatter sunlight as efficiently as micron-sized dust. If the grain size distribution is skewed toward particles that are either very small and quickly pushed away, or very large and too heavy to loft, the visible coma can be weak. In that case, TESS might rightly report a point while infrared instruments describe an atmosphere. Yet the stubbornness of the point invites another layer of care. Even a faint, broad halo can announce itself as a slight thickening of the wings if you stack long enough. Analysts search for that subtle fattening. They test for tiny shoulders on the radial profile that would hint at an extended veil. They do not find a clear shoulder. They ask whether forward scattering near a small phase angle could hide a tail directly behind the core when seen from Earth. Geometry is checked. The viewing angle does not rescue a halo that large. The point sits there like a polished bead. Imagine the craft itself as it swings through its high orbit and sends down orderly swaths of sky. The cameras do not blink. The stars roll. The interstellar visitor writes a straight line across the raw frames, one faint dot per exposure. When the frames are shifted and added, the line collapses into a single point. It looks almost defiant, not a mote, not a smear, a dot that insists on its boundaries. 2 additional facts matter for those who read light as a map. The instrument's response loves steadiness. Systematic errors that can mimic a halo are well cataloged in the mission's manuals and alerts, including scattered sunlight, thermal settling, and detector ghosts. Each of these leaves characteristic patterns that are familiar to the pipeline. None of those patterns match what is seen here. What is seen here is ordinary in shape and extraordinary in context. It is a normal point source where a fluffy comet ought to be. The mind reaches for counterfactuals. If there were a dust cloud so dense and tight that all grains hug the nucleus, could the optical image still look stellar while gas flowed out freely? Gas drag argues against it. Once molecules escape, they push on grains and expand the scene. Radiation pressure then carries the smallest grains away. To pin dust so close that it hides inside a single TESS pixel requires either grain properties that resist acceleration or an active mechanism that constantly sweeps them back inward. The first is unlikely. The second borders on the imaginative. The simplest answer remains that the dust is scarce, dark, or both. Shift to a different register for a moment. There's an old comfort in instruments disagreeing. When an instrument says yes and another says no, the space between those answers becomes the place where new knowledge grows. TESS is a steady hand. Infrared spectrographs have the sharper ears for molecules. Each witnesses a different face of the same traveler. One sees a bead of light. The other hears a whispering cloud. Return to the image that lets the body soften. A moth in the dark seems invisible until a flashlight catches the chalk of its wings. Without the flashlight, it is only the tiniest star against the leaves. TESS is the quiet eye in the park at night. The infrared is the flashlight. Both are honest. Together they outline a stranger. Cluster the remaining technicals, then let them go. The stacking aligns on the ephemeris so the visitor does not smear. The radial profiles are compared to nearby stable stars. The background is modeled with low-order polynomials and checked against empty regions. The residuals show no excess wings beyond what the instrument normally draws. If a coma exists in visible light, it is either too broad and faint to rise above noise, or too chemically different to scatter efficiently. A gentle question closes the circle without urgency. If the gas is there and the dust is not, what does that say about the nursery that shaped this object? Was it formed in a colder ring where water stayed trapped while carbon dioxide vented first? Did it spend long years shielded from starlight, preserving an inventory of volatiles that unfold in a sequence unlike our comets? Or is there a surface crust that locks water down until much higher heat, allowing only the lighter breath to escape in these weeks before closest approach? Hold the dot in your mind. It is small, precise, and oddly persuasive. It asks us to accept that sometimes restraint is the truest signal. To see nothing but a point is not to see nothing. It is to see the instrument tell you, with simple honesty, that in its band and at its scale, the visitor is compact. Later, other senses may fill in the air around it. For now, the point alone is enough to keep the mystery alive. Close the notebook on the visible picture. The red band stays quiet. The star-shaped profile stays narrow. The salt grain rides the belt without fraying. In one register of the spectrum, the cosmos is a study in minimalism. It is a whisper that refuses to become a shout. In the quiet band of heat light, the same traveler blooms. Lines rise where molecules breathe, and the darkness fills with chemistry that optical cameras barely register. Infrared does not care how tight a point looks to a broad visible detector. It listens for specific vibrations, the way a tuning fork rings when it meets its note. Carbon dioxide announces itself around 4 microns. Water answers at shorter infrared wavelengths, sometimes through daughter signs when sunlight breaks it apart. When a spectrum lifts at those places and keeps lifting for hours, the message is simple. Gas is moving. The coma is alive. Imagine a glass sphere you cannot see, the size of a small city, surrounding a pebble that glints. The sphere glows only in heat that human eyes do not catch. A sensitive ear hears it anyway. The ear is the spectrograph, and it begins to map a lantern around a stone. 2 hard facts steady the scene. The chemistry tilts strongly toward carbon dioxide over water by roughly 8-to-1, a ratio far from what most solar comets display when they first wake. The observations run for long stretches, many hours grouped across multiple nights, and the signal stays consistent, which points to sustained outgassing rather than a fleeting flare. There's no quick trick here. It is a durable atmosphere of molecules. The temperature of the grains and gas is low in human terms, close to the cold of deep space, yet still warm enough that carbon dioxide can escape from exposed vents long before water becomes vigorous. That difference matters. Carbon dioxide is a super volatile compared to water ice. It begins to flow under milder sunlight, so a carbon dioxide-rich coma can thrive far from the sun, while water remains more restrained. If you think in layers, one layer has already loosened, while the deeper, wetter layer waits for stronger heat. Cluster the compact numbers and set them down together. Distance at the time of early infrared detections, about 3 astronomical units. Carbon dioxide to water ratio, near 8-to-1. Typical gas speeds in such conditions: a few hundred meters per second. Coma scale, thousands of kilometers across. These are the handles. Hold them briefly, then let the image return. Instruments approach this field with care. Infrared spectrographs subtract the glow of the sky, then fit known molecular fingerprints. If the lines were an artifact, they would shift with the instrument or the background rather than with the moving target. Here they track the object's path. The brightness changes slowly, coherent with the object's rotation and distance. The pattern is not a stray reflection, it is the voice of the molecules themselves. The optical picture and the infrared picture now sit on the same table, and they do not match. In one set of eyes, the traveler is a star-shaped dot. In another, it is a soft-breathing sphere of gas. There is a temptation to force agreement, to argue that one must be wrong. The discipline is to let both be true, then ask what arrangement of matter allows both truths at once. A grounded speculation follows from the physics of scattering and emission. If the gas carries few dust grains, or grains that are dark and large, then the reflected sunlight in visible bands will be faint, even while the infrared lines glow strongly. Dust is the glitter in a visible coma. Remove the glitter, and the light that bounces to optical telescopes collapses. Keep the molecules, and the infrared still sings. Under that regime, the same body can be a tidy point to one instrument and a broad, obvious atmosphere to another. There are natural paths to such a dust-poor flow. A crust can center in the cold, welding grains into a surface that resists lifting. Cracks can open that act more like vents than fountains, letting gas seep without tearing loose much rock. Grain sizes can skew too small to reflect well, or too large to loft easily, leaving the Goldilocks sizes underrepresented. Season can matter too. If only a polar patch is illuminated, a narrow plume can feed a wide, low-density shell that favors molecules over sparkles. Hold a vivid image to take the edge off the puzzle. Think of a lake in winter, sealed by clear ice. From a fissure, the air sneaks out, invisible except in frigid moonlight when the breath fogs. A camera tuned to daylight sees a clean, dark sheet. A camera tuned to that breath sees a dome of vapor slowly rising. Neither camera lies. Each tells a different truth from the same scene. The infrared measurements also trace how energy moves through the coma. Carbon dioxide absorbs sunlight and re-radiates in a set of precise lines. Those lines can be modeled to estimate how many molecules must be present to create them, and to estimate how fast they escape. Put the flux on one side of the equation, put the line efficiency on the other, and the result is a rate that speaks of kilograms per second rather than whispers. The exact figure will swing with assumptions about temperature and geometry, but the order of magnitude is enough. This is not a hint, it is a flow. A second hard fact belongs beside the first. Interstellar history can yield weird inventories. The first interstellar comet we studied in detail carried unusually high levels of carbon monoxide. The first interstellar asteroid showed little dust at all. A third visitor that shouts in carbon dioxide is not an alien rule breaker by itself. It extends a small pattern that interstellar bodies do not always match our solar recipe. The 8-to-1 ratio, though, stands out within that context. It is generous, and it resists easy copying from familiar comets. The mind presses on the mismatch. If gas is this active, why not at least a faint optical fog? Perhaps there is one, spread so thin that it sinks below the surface brightness that a wide pixel can tease out. Perhaps the light is there, but diluted across a scale too large to thicken the wings of a point spread function. Or the dust is present, but coated with compounds that dampen reflectivity. In each case, the infrared wins because it measures emission at the molecule's own note, rather than the sun's reflection off a grain. Another image settles the nerves. Picture a candle enclosed in a clear shell. In daylight, the shell looks empty. In the infrared, the shell glows softly. The wick inside remains a pinpoint in visible light, easy to mistake for a star. The shell is real, yet it belongs to a spectrum the eye was not built to see. A compact technical breath gathers before fading again. Spectral lines at fixed wavelengths tell us which molecules are present. Line widths hint at speeds. Line strengths, after the instrument's sensitivity is accounted for, imply how many molecules are singing. Background subtraction and nodding remove much of the sky's warmth. Calibration lamps and standard stars mark the instrument's response. When the numbers survive that gauntlet, the confidence hardens. That is the case here. The conclusion is a steady, molecule-rich atmosphere that is optically shy. The open question arrives with weight, but not with alarm. If the infrared coma is this strong, while the visible coma stays quiet, what knob on the physics is set to an unfamiliar position? Is the surface tuned to vent gas through narrow cracks that spare the dust? Is the grain chemistry so dark that even a fair amount of dust looks dim? Or is the gas engaging in plasma behavior that changes how dust decouples from flow, keeping grains closer to the core than our simple models expect? For the listener drifting at the edge of sleep, it helps to keep one idea close. Instruments do not disagree to frustrate us. They disagree to draw the map in relief. High ground and low ground become clear only when light and heat sketch the same terrain from different angles. In those differences, the shape of the traveler emerges. We now have two honest portraits on the table, a tidy optical point and a generous infrared lantern. In the next movement, we test the natural fixes that could reconcile them, starting with dust that clings too close, geometry that flatters a point, and the suspicion that activity flickers only when we are not looking. The closer it drifts, the sharper the questions cut. Picture a cold kernel wrapped in something that refuses to shine. If dust is there, it clings like a shadow, hugging the core as if pinned by an unseen hand. A tidy explanation tempts us. If the dust never leaves the neighborhood of the nucleus, then an optical camera with generous pixels will keep seeing a point, while infrared spectrographs record a living coma of gas. The story would be simple. Gas flows. Dust stays home. TESS smiles at a star. JWST hears the breath. The trouble begins the moment we ask whether dust can actually be forced to behave that way. Fresh gas does not leave quietly. Sublimation at sunlit cracks builds a pressure that negotiates with gravity, cohesion, and inertia. On small bodies, the gravity is weak. Cohesive forces between grains can be weak or strong, depending on how the surface sintered through long winters. If cohesion is modest, gas drag lifts grains and gives them to radiation pressure, which then carries the smallest grains downwind. If cohesion is large, gas can percolate through pores and fractures without entraining much solid material. Both regimes exist in the comet literature. Neither yields a perfect halo that sits tight like a painted collar, unless something special is going on. Hold a simple image. Lift the lid on a porcelain teapot in winter and watch the steam curl through a hairline crack. If the crack is narrow, vapor escapes without throwing chips. The pot stays clean even as the breath is obvious. A nucleus covered by a durable crust can behave like that. Gas finds paths of least resistance. Dust does not follow. The coma becomes molecule-rich and grain-poor. Two hard facts help us test whether such restraint could hide inside a TESS pixel. First, a TESS pixel spans roughly 21 arcseconds. At a distance of about 3 astronomical units, that translates to close to 50,000 kilometers. A coma smaller than that footprint can merge into the instrument's point spread function and look stellar. Second, typical gas speeds for carbon dioxide at those distances are a few hundred meters per second. which let molecules fill a sphere that is thousands of kilometers across in short order. The scale of the gas envelope is easily big. The question is whether the dust cross-section remains small enough to stay visually shy within the same footprint. Cohesion gives one path to shyness. Rosetta's instruments measured tensile strengths on a well-studied comet in the range of tens of pascals. In that regime, a crust can hold back grains, while gas slips through pores like wind through reeds. Laboratory studies and thermal models show that crusts can anneal, sinter, and seal under repeated sun. If 3IATLAS carries a crust that formed in a different nursery, with different organics and salts, its pores may be stingy. The gas flows. The glitter does not. Gas composition gives a second path. If the volatile leading the output is carbon dioxide instead of water, the energy budget and drag physics shift. Carbon dioxide begins to work at lower temperatures than water ice. It can feed a coma when sunlight is still mild, and it can do so through narrow vents that do not carve fountains. A narrow vent can make a broad, low-density shell without tearing loose a blizzard of grains. The optical cross-section stays small. The infrared lines stay loud. Grain size distribution adds a third knob. Optical brightness cares about total reflective area. If the distribution is skewed toward grains that are very small and blown out quickly, or very large and heavy enough to stay seated, then the sizes that scatter sunlight efficiently can be underrepresented. In that case, the visible coma is faint by design. The gas can cradle a shell. The shell can be there. The shell can be shy. Now the counterforces. Even through pores and cracks, a vent that runs for hours will usually drag some grains. The smallest grains need very little push to lift. Once free, they are hard to keep local. Radiation pressure acts on their broad area relative to mass and nudges them outward. Even if a crust keeps most grains trapped, the leftovers should still fatten the wings of a stacked optical profile. When careful analysts look for that fattening and do not see it, the dust-packed hypothesis has to work harder. Electrostatics sometimes enters these arguments. In bright sunlight, photoelectric charging can loft the tiniest grains above a surface and then make them settle again. Near perihelion, plasma effects can draw a sheath around a nucleus and change how grains couple to the flow. These effects can keep grains close for a time, or move them in ways that do not simply radiate outward. The key phrase is "for a time." The habit of a comet is long. If the coma persists night after night, the anomalies must persist too. Gather the compact technical breath, then release it. Pixel scale near 21 arcseconds. Projected footprint near 50,000 kilometers at 3 astronomical units. Gas speeds a few hundred meters per second. Tensile strengths on fragile crusts around tens of pascals. Typical dust albedos low enough that dark grains reflect poorly. None of these numbers in isolation decide the case. Together they map the playing field. The most natural version of a dust-packed near core looks like this. A stiff, dark crust fractures along narrow seams. Carbon dioxide vents through those seams and inflates a wide, molecule-rich shell. The pores and fractures are too stingy to tear loose much dust. The dust that does escape is either too dark, too big, or too small to add much optical sparkle. The optical radial profile stays clean. The infrared lines sing. There is an alternate natural picture that sounds neat but breaks on closer inspection. Suppose a very dense dust cloud hovers near the nucleus, held there by some balance of gas drag inward and radiation pressure outward. The balance cannot last. Gas streaming out exerts a net push away from the core. Even if grains recirculate within caverns and vents, once they enter the open coma, they drift, trapping them within a footprint tens of thousands of kilometers across for many hours. While gas escapes briskly asks for a tuned mechanism that nature rarely provides. Return to a scene that steadies the pulse. Think of talcum powder on a cold glass plate. You blow across the surface. Most grains slide. A few stay, glued by a trace of moisture. The plate fogs. From far away under a street lamp, you see the fog first. The powder reads as nothing. If your camera is tuned to fog, you record a dome. If your camera is tuned to chalk, you record a point. Two more facts belong on the table. Historically, comets with very low dust-to-gas ratios have been measured, and they often look unimpressive in small telescopes while sounding strong in gas-sensitive instruments. Also, phase angle can amplify forward scattering from dust. But when geometry is not extreme, the effect cannot erase a substantial coma that sits right against a bright core. When analysts fold in the viewing geometry and still cannot coax a wing into the profile, the clean point becomes meaningful. Where does that leave the dust-packed hypothesis? Not dead, not triumphant. It survives in the narrow lane where a stiff crust, a carbon dioxide-heavy inventory, and an unhelpful grain-size distribution combine to keep the optical cross-section low. This lane is not the median of comet behavior, but neither is an interstellar traveler obliged to be median. The hypothesis works best if the surface is young to sunlight, with vents that have not yet eroded into broad fans. It works best if the dust is dark enough to damp the reflectivity. It works best if the grains that would have glowed in visible bands are underproduced. A grounded speculation presses a little further. If gas is ionizing near the nucleus, a thin plasma sheath can form that changes drag on the smallest grains, even pushing some back toward the surface briefly before they find a path outward. That kind of near-core choreography can keep the first few hundred kilometers unusually clean of glitter while gas heads for larger scales. The effect would not last forever, but it could last long enough for a campaign of observations to record a point where a smudge was expected. One question remains and does not loosen quickly. If dust is truly that restrained, why do we not see even the faintest brightening of the point's wings after stacks that run through thousands of frames? Do we accept that the coma is so broad and dilute in visible light that it hides in the background? Or do we begin to admit that what surrounds the core in infrared is not behaving like a classic dust coma at all? Vivid image brings the pacing down. A frost field under pre-dawn stars holds its breath. Air slides through hairline cracks in the ice and builds a low dome of fog that only the right lamp reveals. From a distance, it looks like nothing. Step closer with a thermal camera, and the field breathes in slow, even waves. The practical test is simple to write and harder to meet. If this is a dust-poor coma, then polarimetric measurements at visible wavelengths should show a muted signature compared to a dusty comet at the same solar phase. Deep imaging with finer pixels should either reveal a faint veil on scales smaller than the TESS footprint or confirm the cleanliness of the immediate neighborhood. If both tests keep returning emptiness, then the dust-packed answer will have done its duty, and we will need another door. Angles cheat the eye. Even honest light can mislead when tail, sun, and observer fall into neat lines. Geometry is a conjurer, but its tricks have limits. Begin with the simplest deception. If a plume points almost directly at us, a broad structure can collapse into a tight core. A thin pencil of dust aligned along the line of sight will stack its glimmer on the nucleus and look compact. The idea is elegant, almost soothing, because it asks nothing exotic from the traveler, only positioning. Yet comae are not needles, and time is cruel to coincidences. A spherical gas shell surrounds the first hundreds or thousands of kilometers around most active nuclei. Even if a jet aims our way, the near-core envelope still fattens the profile. Over long integrations, spin and sunlight change the angle. A perfect alignment that remains perfect for many hours begins to sound less like geometry and more like wishful thinking. Consider phase angle, the sun object observer angle that sets how dust scatters invisible light. Dust can prefer certain angles. At some geometries, it backscatters and softens the scene. At others, it forward scatters and brightens the halo. But the effect modulates. It does not erase. A generous coma at a modest angle still glows. A near empty one at a favorable angle still stays subtle. Geometry can season the optical brightness. It rarely turns a feast into an empty plate. Parallax also tempts as an answer. TESS rides a high Earth orbit. JWST keeps station near the Earth-Sun L2 point, roughly 1.5 million kilometers from Earth. Two observatories separated by that baseline do see slightly different scattering angles and solar elongations. The difference in view is real, yet small compared to astronomical distances. When both instruments observe the same nights, a few degrees of phase change cannot convert a broad coma into a star-like dot. Parallax does not rescue the paradox. It gives you tweaks, not transformations. Another geometric refuge is glare and background structure. Perhaps the optical field was messy. Perhaps a star field or scattered light smeared a faint halo into the noise. Deep stacks are designed to tame that kind of clutter. Analysts select clean patches, model the background with smooth surfaces, subtract known ghosts, and compare the target with nearby stars that share the same optical path. These rituals do not make miracles. They make confidence. When the target still looks as narrow as the instrument's fingerprint, the tidy shape is telling us something about the target, not about the corner of the detector. Imagine two sentinels at different windows of the same house. One faces a sunlit yard and sees only the shine of a nail head on a fence post. The other looks through a thermal pane and notices a soft breathing around that nail, a little halo of heat. Neither sentinel is lying. The yard's glare hides the breath. The heat window reveals it. Both are looking at one visitor standing very still. Two hard facts keep the discussion honest. Gas emission lines in the infrared do not depend on reflected sunlight. They are molecules radiating at their own notes. So phase angle and dust color barely touch them. Visible brightness from dust, however, is one long act of reflection, built from grain albedo and scattering function. A second fact is that comae near the nucleus are close to isotropic on small scales, unless activity is confined to a pinhole. Even then, rotation and sunlight shift the plume. A telescope that watches for hours should inherit some widening from that near-core region if dust is present in ordinary amounts. Now press on the special cases. Could the tail align with the sun so precisely that forward scattering throws most of the dust light away from us, while the gas shell remains optically thin? It is possible in short stretches, but the symmetry breaks when the nucleus turns, when the subsolar point shifts, when the projected velocity across the field changes. To preserve a perfect trick across many nights means locking several moving parts into one pose. Nature almost never holds still that way, especially near perihelion when torques and day-night cycles become lively. Could the coma be flattened into a sheet by solar wind flow and then tilted so that we view the sheet edge on? Plasma interaction can indeed sculpt a comet's environment. Contact surfaces, ion tails, and draping fields produce elegant shapes. Those shapes, however, live in the realm of charged particles and light ions. The dust that paints optical frames is heavy and sluggish by comparison. It does not laminate itself into perfect sheets that stay razor thin. Even when the plasma carves the gas, the dust tells its own slower story. Gather the compact numbers, then let them go. L2 sits about 1,500,000 kilometers sunward of Earth. The relevant phase angles in routine interplanetary viewing wander by tens of degrees, not hundreds, when two near-Earth observatories look at the same object in the same week. The near-core coma, where an optical profile learns to swell, spans thousands of kilometers even at modest gas output. Each figure is rounded, each figure sufficient for scale. None supports a geometric switch that flips a storm into a star. There is a more subtle optical path, and it deserves a fair hearing. Dust grains are not uniform pebbles. They are clusters of smaller pieces, sometimes coated with organics that absorb blue light more than red. Their scattering can favor some directions and punish others. A grain population that happens to dislike the specific sun observer angle during the TESS campaign would look dimmer than usual in that band. If the same grains radiate thermally right, where an infrared spectrograph listens, then the infrared still rises. This is not magic. It is how microphysics makes preferences. But preferences bend light. They do not arrest it completely. Even poor scatterers give you a little haze, if there is enough of them. Return to a steadying image. A waterfall seen head-on looks like a silver cord, thin and precise, until you step to the side. Then the hanging sheet reveals itself, wide and loud. Geometry writes illusions, but the waterfall is always a sheet, never a thread. If you spend all afternoon facing it, the breeze will even do the stepping for you. The grounded speculation sits here. If a thin plasma sheath near the nucleus is influencing how charged dust couples to the flow, it could channel the smallest grains along magnetic field lines and bias their motion toward directions that lessen visible scattering in our line of sight. That would be a physics knob beyond simple geometry, and it would affect optical appearance without silencing infrared lines. It would also require a consistent magnetic and electric environment, which sounds more like an engineered stability or a rare natural harmony than a common state. There is also the possibility that our eyes are correct in both bands and that the geometry is fine, but the coma is not dust in the common sense. If the envelope is molecule-rich and genuinely dust-poor, then the optical camera has nothing to scatter. That option returns us to material inventory, not angles. Two more hard facts anchor the end of the argument. Rotation periods on small bodies are measured in hours, so jet directions wander across a night unless the active region sits at a pole pointed just so. And when an optical profile refuses to grow wings after thousands of stacked exposures, any explanation that leans on temporary alignment needs to explain not one lucky pose, but many. The mind likes simple explanations, and geometry is simple. It feels gentle to say that a trick of the angle made a halo vanish. The evidence asks for more spine. The optical point persists too neatly. The infrared lantern speaks too clearly. Between them, angles and parallax look like minor edits, not like a hidden author. One last image smooths the breath. Picture a lighthouse on a foggy coast. From far along the shore, you see only the bright bulb, a clean dot. Walk toward the cliff and the fog thickens into a wall that glows in the beam. The cliff did not move. You moved. Geometry changed the mood, not the truth of the fog. A small cluster of tests can keep us honest. Polarimetry in visible light would measure how grains align with angles. A muted signal supports a grain-poor coma rather than a geometric trick. Synchronized observations from multiple longitudes would watch for rotation-driven changes that geometry cannot disguise. Thermal imaging at shorter optical wavelengths would test whether any hidden forward scattering still betrays a veil. The question remains calm and sharp. If angles cannot disguise a large, dusty halo for this long, what physics lets the same body read as a point in one register and a lantern in another? The map of excuses grows thin. For a tidy answer, we wish for a switch. On means coma, off means star, but the light refuses to click. It hums, steady, as if the switch were an old lie. Long integrations make or break the flicker idea. If activity were blinking, optical stacks would thicken on some nights and thin on others. Infrared lines would surge, then fall quiet. Instead, each camp reports constancy at the scale their instruments can feel. The optical profile stays narrow through deep stacks collected across multiple nights. The infrared bands hold their brightness for similarly long stretches. The paradox does not pulse, it endures. Imagine a lighthouse whose lamp never wavers while fog rolls in slow, even tides. From the cliff path, the bulb is a clean bead of light. From the beach, the fog glows as a soft wall. Hours pass. The bead stays sharp. The wall stays patient. Nothing blinks that should not. Two hard facts keep the argument honest. First, sublimation responds to sunlight and surface temperature with inertia, not like a light bulb. Ice warms by degrees and exhausts by degrees. Minute-to-minute flicker is rare unless vents are tiny or unstable. Second, rotation on small bodies often lives on the scale of hours. As faces turn into daylight, a plume grows, then shrinks. That modulation paints gentle waves, not violent jumps. In the infrared lines and in the overall coma brightness, if a sharp on-off pattern exists, it should leave fingerprints. Those fingerprints are faint to absent. Cluster the compact numbers in one breath before letting them go. Observation runs last for hours at a time and repeat across several nights. Rotational periods on cometary bodies commonly fall near single-digit or low double-digit hours. Thermal skin depths under sunlight are measured in centimeters, which smooth, sharp temperature shocks. Outgassing rates vary within a day, yet rarely drop to zero when the object is already warm. Keep the scales rounded. Keep the picture simple. So why does the flicker theory cling? Because it is comforting. A switch rescues both datasets. Optical caught the off cycle. Infrared caught the on cycle. The calendars then conspired. But the logs do not reward this comfort. The optical saw a point again and again over long stacks. The infrared saw lines again and again over long integrations. Neither team recorded the jitter an on-off narrative demands. There's a quieter possibility, not on and off set. The source of gas may be geographically fixed and modest. A single vent or a narrow fracture breathes without hiring much dust. Gas escapes and fans into a wide, low-density shell that the infrared loves. The optical band sees a low surface brightness wash that dilutes across a footprint larger than a generous pixel. The coma is active but optically shy by design. In that case, stability across nights is not a problem. It is exactly what the physics predicts. A second possibility lives closer to the nucleus. If the grains that would scatter sunlight while sunlight most efficiently are underproduced, the mid-sized glitter that makes ordinary comets obvious, then optical brightness collapses even as the molecule count grows. Very small grains get pushed out and diluted quickly. Very large chunks stay seated. The middle ranks that make halo sparkle are simply rare. Rotation then modulates little more than the line shapes in the infrared, while leaving the visible profile stubbornly star-like. Hold a vivid image that lowers the pulse. Think of a winter greenhouse lit from inside. Through tinted glass, you see a single bulb, steady and small. Step into infrared, and the entire pane glows with plant breath and warm mist. Return outside. The bulb remains the only obvious light. No one has switched anything. Two senses just favor different truths. The logic presses hard on a third road that sounds clever and usually fails. Microbursts. In this story, the object coughs in short spurts that infrared integrates into a plateau, while optical stacks misaligned in time, smooth into a point. For this to hold across many nights, the coughs must recur with just the right cadence to average out in one pipeline and stack up in the other. That precision borders on choreography. Nature enjoys rhythm, but this would require drumline perfection. The data suggest a drone tone instead. 2 more facts, then a breath. Even when activity modulates with rotation, the near-core gas environment remains present, and dust coupling to that flow leaves traces unless the dust inventory is low. Also, once volatiles are warmed and pathways open, they do not close instantly when night falls. Thermal inertia keeps the surface breathing. That is why coma linger after sunset on a rotating body. A clean point night after night is not the signature of a breathing that halts between one exposure and the next. Grounded speculation leans toward a decoupling of roles. Gas flow is real, robust, and molecule-rich. Dust production is suppressed by crust strength, pore geometry, or inventory. The 2 clocks, gas and glitter, are out of sync. The infrared hears the clock that ticks. The optical waits for a hand that has not yet moved. This is not on versus off. This is one system in 2 registers, both stable, both sincere. A gentle question remains and sharpens the path ahead. If both signals are steady, what couples the gas so loosely to the dust? Is the surface sintered into plates that vent through hairline cracks? Are grains coated with organics that swallow visible light and give back little? Is a near-nucleus plasma changing how fine particles feel, drag and charge so that they hover, fall back, or depart in directions that keep their visible glow thin? Picture the traveler at dusk in its own small day. A bright seam warms and whispers, gas threads outward and becomes a cold balloon. The nucleus rolls. The seam dims a little and waits for morning. The balloon never fully collapses. Nothing about this cycle requires a light switch. Nothing about it demands drama, yet to 2 different senses. Optical for sparkle, infrared for song, the scene splits into a bead and a lantern. Before we leave the flicker idea behind, a compact test list can anchor the mind. High cadence infrared time series can search for rotation scale waves in line strength. Simultaneous optical polarimetry can probe for the faintest dust signatures that a simple profile misses. Coordinated nights across longitudes can watch for changes geometry cannot fake. If the story is on and offset, not on and off, these tests should settle into patterns rather than spikes. The switch theory fades. What persists is a single body that behaves as if 2 systems overlap. A compact, quietly reflective heart wrapped in a broad, molecule-rich breath. To follow that hint, we turn next to the dual-state picture itself, where core and mantle share one address while showing 2 faces to our different senses. Night favors the quiet voice of paradox. A single traveler glides sunward, yet our instruments paint 2 portraits. One is a polished kernel that refuses to spread. The other is a pale breathing envelope that answers to heat and light as softly as a tide. Consider the simplest union that respects both views. At the center sits a compact core, bright enough to look stellar in visible bands, and small enough to fit entirely inside a generous pixel. Around it, a low-density mantle of molecules and faint ions swells to city scales, radiating at its own favorite notes in the infrared. The core offers sparkle, the mantle offers song. Put the 2 together and the scene becomes bead within aurora, one image nested inside another. What could make a mantle glow while hiding from visible eyes? Molecules do not need sunlight to bounce off a grain. They need only the right energy to vibrate and rotate. Carbon dioxide provides that energy path at mid-infrared wavelengths. Water has paths of its own. When radiation from the sun and the warm nucleus pumps these modes, The molecules answer with narrow lines that an infrared spectrograph can catch and count. The visible band, by contrast, wants surfaces that scatter. If the coma is dust poor, or if its grains are dark and large, then the scatter grows thin even while the infrared grows bold. The mantle becomes a whisper in one register and a chorus in another. Now ask how the mantle and the core might decouple. Start near the surface. A crust that has sintered through long winters can become tight and strong. Vents open along hairline seams rather than wide fans. Gas squeezes through those seams and expands, but the flow carries too few grains to paint the optical field. At the scale of a few hundred kilometers, the mantle is already close to isotropic, a soft balloon of gas and light ions. The balloon keeps growing, only restrained by sunlight and escape speed. The core remains a pin. The balloon does not register in visible light because it is poor in glitter. Add the near-nucleus electricity that sunlight writes. Photoionization strips electrons from some molecules. Solar wind can push a sheath of charged particles into layered shells around the core. In such an environment, the smallest grains pick up charge quickly and feel forces that do not always point the same way as gas drag. Some grains settle back. Some grains slide along field lines before leaving. The net effect is a near-core zone that is less friendly to the mid-size glitter that visible bands love. Out beyond those first few hundred or thousand kilometers, the coma is gas-dominated and grain-shy. Infrared thrives there. Visible light does not. Two hard truths sit at the center of this picture. First, the optical profile matches a stable point spread function through deep stacks and across more than one night. A halo of ordinary dust should have fattened the wings by at least a trace. It did not. Second, the infrared lines persist for hours with a heavy tilt toward carbon dioxide over water, near 8:1 by simple ratio, which is high by comet standards and steady in time. Taken together, these truths reserve a seat for a small, reflective, or at least compact core inside a wide, molecule-rich envelope. They do not insist on a common dust story for both. If that is the geometry of matter and light, a short list of predictions follows. The visible polarization signal should be muted compared with a dusty comet seen at a similar phase angle. Narrowband filters that isolate common radicals like CN or OH may return only shallow features, while bands centered on carbon dioxide products in the infrared keep rising. When the object rotates, the infrared should breathe a little, but the optical profile should mostly stay narrow, because the part that widens it remains weak. Collect a compact moment of numbers, then let them drift. A pixel footprint near 50,000 kilometers at the distances involved. Gas speeds near a few hundred meters per second. A mantle scale of thousands of kilometers within hours. A ratio of carbon dioxide to water near 8. A rotational timescale likely in single-digit hours or a little longer. These handles are round and gentle. They are enough. Return to the face at the center. The optical core could be bright because it is reflective, perhaps coated in frost or salts that happen to favor the red band where the detector is most sensitive. It could also be merely compact, a geometric point relative to the instrument's scale, and not necessarily a high albedo shard. Either way, the message is the same. In visible light, the traveler is small and tidy. The shadowy breath around it is too faint to thicken the wings. The mantle itself can be thought of as a soft chemistry engine. Carbon dioxide escapes first from deeper pockets, because it asks less heat to leave. Water follows later as fractures widen and the subsolar region warms. If vents are few and narrow, grain lifting remains weak, which preserves the mantle's invisibility to wide visible pixels. The mantle glows the way warm mist glows when a night scope translates wavelengths into quiet light. The core shines the way a steel bead shines under a lamp. Both can be truthful at once. Imagery helps the nerves relax. Picture a firefly sealed within a clear sphere. In daylight, from far away, you see only the tiny point of the insect's lamp. Through a thermal window, you see the shell faintly lit by breath and motion. Step back to the first view, and the shell fades again. The firefly did not change. Your senses changed. The decoupled model also fits the rhythm of interstellar travelers we have met so far. One was rich in unusual gases. Another lacked a clear coma in ordinary light. A third that carries strong carbon dioxide and little glitter would extend, not overturn, that small pattern. Interstellar nurseries assemble ice and rock in recipes that do not have to match the mixtures near our sun. A high carbon dioxide inventory, preserved in deep cold and released through narrow seams, becomes less surprising under that lens. Skeptical minds deserve more than pictures. The model should face tests. Deep, visible imaging with finer pixels ought to find either a faint veil just outside the immediate core, or confirm a stark cleanliness over tens of thousands of kilometers. Ultraviolet searches for hydroxyl or other daughters would reveal whether water is truly suppressed or merely hiding behind a geometry of light. Low-frequency radio observations can probe the plasma sheath, since even a thin mantle of ions and electrons leaves signatures in wave behavior near the nucleus. Each test is patient. None requires drama. A different quiet suspicion sometimes creeps in here. If the mantle carries mostly molecules and few grains, why does the infrared not show a thermal continuum from dust that still exists in small amounts? The answer is degree. A small continuum may well be present, but the lines are strong enough to carry the day. When the line emission is robust, the continuum can be honest and still be second place. The instrument hears the melody first, then the faint hum beneath it. There is one more door to check before we leave this room. Could the two faces belong not to two states of one body, but to two bodies in close company? A fragment pair within a tiny separation could, in principle, let one behave like a compact reflector, while the other behaves like a gas source. The problem is motion. A bound pair that close would tug on each other in ways that change the light curve or the centroid subtly across hours and days. Careful centroid checks and photometric stability argue against near companions bright enough to matter. The simpler answer still fits best. One nucleus, two behaviors. Let a final image slow the breath again. Think of a pearl inside a bell jar. To the naked eye under room light, the pearl is all you see, small and definite. Switch to a camera that sees warm air, and the bell jar suddenly glows. A faint dome around the bead. Step back to room light, and the dome vanishes, though the air still moves. The pearl has not lied. The jar has not lied. The senses have agreed to divide the labor. In that spirit, the dual-state picture respects the data without force. The visible band attends to the compact heart. The infrared attends to the wide, molecule-rich breath. As perihelion approaches, heating should nudge the balance. If vents widen and water joins more strongly, the optical veil may thicken a little, and the ratio of gases may slide toward a gentler split. If the crust stays stingy and the chemistry stays unusual, the two faces may persist. Either path can be measured. Either path will teach us which knobs truly control light and matter in a traveler born far from home. Heat changes the script. Near the sun, quiet materials choose new names, and the same body begins to look unlike itself with each new turn of light. Imagine a sealed rind that has traveled for ages through deep cold. It carries pockets of supervolatile ice. streaks of brittle salts, and islands of darker crust welded by time. Far from the sun, the Rhine sleeps. Nearer, it learns the grammar of noon. Warmth does not arrive like a switch. It arrives like a tide, shallow at first, then deeper, wave after wave. Each wave sinks a little farther. Each wave finds a new seam. Begin with the most patient physics. A surface cools and heats across a skin only a few centimeters deep. That thin layer lives on a clock of hours, not seconds. Inside it, ices do not simply melt, they reorganize. Amorphous water ice can rework itself into a crystalline lattice and release trapped gases as it does so. Carbon dioxide can begin to sublimate at lower temperatures than water. The order in which these doors open matters. A body that was optically quiet when colder can turn out to be chemically busy once carbon dioxide finds a path outward. Now picture the crust as it learns that new schedule. Sunlight probes a fracture left by an ancient impact. That line warms first. Along it, bonds that winter welded begin to unhook. The seam widens by hair widths. Gas pressures inside reach for that path and take it. The flow starts thin, then steadies. It is not a fountain, it is a breath. Because the opening is narrow and set in strong material, it carries mostly molecules and few grains. The infrared reads a halo of life. The visible band keeps its clean point. Nothing contradictory has happened yet. The body is simply passing through a stage where chemistry escapes faster than glitter. Two hard facts keep this picture grounded. Perihelion arrives on October 29th, the day when solar heating will peak and the sequence of phase changes will run at its quickest pace. The chemistry already tilts toward carbon dioxide over water by something like 8-1, which is unusual but not without precedent for distant, cold-born material. Put those facts side by side and a path appears. A carbon dioxide first regime is already in motion. Water may follow if vents widen or new ones open. Cluster a compact set of numbers and put them down together. Skin depth on daily timescales, centimeters. Gas speeds close to a few hundred meters per second. Stresses that weak crust can withstand, measured in tens of pascals. Rotational periods for small bodies, commonly hours. Perihelion timing, late October. Each number is rounded. Each number plays well with the idea that slow heating and narrow vents can keep the optical scene tidy, while the infrared grows louder. Metamorphosis helps explain rhythm. As heating grows, gas pressure under plates can lift them slightly, then let them settle again when night cools the seam. It is a soft version of tectonics, without plates that drift for miles, only flakes and shingles that lift and fall. When a flake lifts, fresh interior ices touch space, and the flow increases for a day. When the flake drops, the flow lowers, but does not vanish. Add rotation and the subsolar spot wanders. The vents trace small loops of action across the surface, always breathing, never raging. To optical eyes that want dust, little changes. To infrared ears that want molecules, the melody lengthens. Sintering enters next. Under repeated warmth, a porous crust can anneal. Pores narrow, necks form between grains. The surface becomes more like pottery and less like snow. This reduces dust erosion and favors slow gas seepage. In that condition, a traveler can assemble a vast, low-density envelope without ever throwing much powder. A halo forms that looks like a ghost to visible light, but feels dense to a spectrograph tuned to a molecule's note. Hold a vivid image. A walnut sits in a slow oven. The shell darkens and develops a hairline along old growth rings. When the line finally opens, it does not explode. A thin ribbon of steam escapes. To the eye across the room, The nut is a dark bead that glints. To a thermal camera, a faint dome forms around it, rising and thinning with each gentle breath. The two instruments are right at the same time. As perihelion nears, new behaviors can layer on top of the old ones. Sublimation torques spin up small bodies over weeks. If spin increases, slopes that once held their rubble begin to ease downhill. Landslides can expose patches of fresher frost. A young patch may briefly brighten the visible band, then fade as it crusts over. The net effect is not a sudden glare. It is a pattern of tiny awakenings that keep the infrared coma strong, while the visible still resists wings. Thermal cracking adds another channel. Repeated day and night cycles open and close fractures, deepening them a little each time. The cycle is patient. It does not carve a canyon in a day. It does what ice does in mountains. It pries. Where the prying connects to a cavity, pressure has a chance to build. Where it connects to a shallow seam, gas can skim under the surface before lifting off. Both modes help the coma without hiring much dust. Two more hard facts give spine to the metamorphosis story. Gas-dominated comae have been measured before around bodies with low dust-to-gas ratios, and they often look unimpressive in small optical apertures while their spectra glow. Also, the coupling of dust to flow is sensitive to grain size and cohesion. If the mid-size grains that would reflect efficiently are underproduced, optical brightness falls even when total mass loss rises. The object can be in a more active state by mass and still appear visually restrained. With these pieces, the transformation reads less like magic and more like order. From far out, the traveler looks like a compact glint because the mantle is thin. Closer in, supervolatiles begin to drive a wide shell that radiates in the infrared. The mantle grows while remaining almost invisible to a generous optical pixel. Nearer still, small patches of water ice may wake and add their voice. Whether this last step happens before or after, perihelion becomes the quiet question that will decide how quickly the two bands begin to agree. Gather one more compact technical breath. The energy balance near perihelion can increase the surface temperature by tens of degrees over what it was weeks earlier. That increment is enough to shift a carbon dioxide first coma toward a mix where water and carbon dioxide share the load. If vents widen, dust lifting can cross a threshold and produce a visible haze. If vents remain narrow and the crust hardens, the optical scene can remain almost unchanged while the infrared climbs a little higher. There is a different, quieter edge to metamorphosis. Plasma forms near active comae as photoionization and the solar wind help charge the flow. Even a thin sheath can alter drag on fine grains and let them settle back for a time. Such a sheath does not need to be dramatic to matter. It only needs to persist near the core and discourage the glitter from forming a concentrated halo. In that environment, chemistry can prosper while optics starve. The grounded speculation is modest. 3IATLAS may be moving through a stage transformation that our instruments catch in slices. Stage 1 is a compact, optically tidy traveler with minimal dust. Stage 2 is a wide, molecule-rich envelope driven by carbon dioxide. Stage 3, which perihelion might initiate, adds water and possibly a little dust while leaving the core still sharp. None of this demands exotic engineering. It demands a crust with a stubborn personality, a chemistry that favors early carbon dioxide, and a sun that does what it always does when distance shrinks. One question remains and carries the right weight for a sleepless mind, easing toward rest. If the crust yields by sheets rather than chunks, and if chemistry prefers gas first, will the visible view stay quiet even as the infrared roars? Or will a single afternoon near perihelion lift a veil and let both senses finally see the same design? Three explanations rise when patience with tidy answers runs out. a cloak that hides, an engine that steers, or a plasma that organizes itself into a quiet, invisible wall. Picture the cloak first, not fabric, but physics. A shell that drinks starlight and gives back almost nothing in the visible band, while venting molecules that sing clearly in the infrared. If someone wanted a passing object to look like a comet at a glance, they would let gas escape and keep glitter scarce. A spectrum would show active molecules. A broad pixel would still see a point. The disguise would be statistical, not theatrical. A veil tuned to wavelengths rather than paint. Two hard facts help this picture stand. The chemistry already leans toward carbon dioxide over water near 8:1, which means a gas that radiates strongly at its own notes, without needing a storm of reflective dust. And the optical profile remains compact after long stacks, which means the glitter that would smear a point is genuinely missing or diluted. A cloak that masks scatter while allowing breath would exploit those same facts. Yet extraordinary ideas should buy their way in with predictions. A technological shroud would likely show control. Gas output would modulate in crisp rhythms that do not track simple day and night on a rotating body. Isotopic ratios might fall outside familiar comet ranges. Narrow jets might hold direction too steadily across many hours. If such signatures fail to appear, the cloak returns to the shelf with thanks for the drama. Now consider an engine with no moving parts, only pressure. Narrow vents act like thrusters. Carbon dioxide escapes and pushes back on the core. The push is small, but over days it adds up. If vents are few and nearly aligned, the net force could be measurable as a slight drift from a purely gravitational track. The same scheme could also help hold dust close, since the flow near the throat is organized and strong, while the total glitter remains low. The optical point survives. The infrared stays loud. The test is astrometric. Measure the path with care and look for a tiny, steady bias toward the direction opposite the dominant vent. A natural plasma offers a third road that asks for no engineering, only sunlight and gas. Molecules leave the surface, some are ionized by radiation, and solar wind drapes magnetic fields around the coma. Close to the core, charged particles can arrange themselves into layered regions. In those layers, forces on the smallest grains do not point the same way as the gas flow. Some grains are nudged sideways along field lines. Some settle back. The near-core volume becomes poor in the mid-size glitter that would widen a radial profile, even while the gas keeps expanding and glowing in the infrared. The result is bead within lantern, written by electricity rather than craft. Hold a vivid image. A pearl sits inside a clear globe on a dark table. Under room light, you see only the pearl, small and definite. Switch to a heat camera and the globe appears. A soft dome traced by breath. Step back to room light and the dome vanishes again. The pearl never moved. Your senses chose which world to show. Two more facts lend spine to the plasma lane. Spacecraft have flown through cometary coma and measured boundaries where the magnetic field and the flow separate, regions that can be tens to hundreds of kilometers across near modest activity. And neutral gas does not care about phase angle when it radiates at its own infrared lines. So the usual tricks of geometry that brighten dust do little for molecules. A quiet plasma that rearranges tiny grains while leaving the gas to sing would point in exactly this direction. This is where the month space weather becomes a clever misdirection. When the sun gusts, ion tails whip and glow. Forecasts talk of geomagnetic storms, and the sky throws auroras far from their usual homes. In that noise, a thin sheath near 3IATLAS could strengthen or relax without giving us the courtesy of a clear baseline. A novice eye might blame or bless the object for a change that came from the wind. Cosmic counterpoint is not just poetry, It is how the background argues with the foreground when both are alive. Cluster the compact technical breath, then let it fade. A carbon dioxide to water ratio near 8:1 tilts the coma toward lines that infrared loves. Plasma boundaries near active comae can sit within a few hundred kilometers of the nucleus. Tiny non-gravitational accelerations from jets can shift a path by a measurable fraction of an arcsecond across weeks. None of these numbers needs to be sharp. They are handles, not nails. Grounded speculation ties the three roads to tests you can do. For a cloak, watch for unnatural regularity in gas rhythms or for chemical fingerprints that do not fit cold birthplaces. For an engine, fit the astrometry and see whether a small thrust direction holds over many nights in the solar frame. For a natural plasma, seek radio and in situ style signatures by proxy, such as faint low-frequency wave activity or subtle changes in polarization that track solar wind conditions rather than the object's rotation. There is room for dry humor in the middle of all this seriousness. If an interstellar traveler decided to wear a costume, it chose one that fools only certain cameras, and only for a season. That is an odd way to hide. Nature, on the other hand, delights in costumes that appear whenever light, charge, and flow share a room. The simpler playwright usually wins. One more image slows the breath. Think of a candle behind smoked glass. In daylight, you see only a point of flame. In the right infrared band, the glass itself glows. If the glass has a faint charge, ash clings or falls in patterns that shape the glow without changing the flame. Switch windows and the story flips. The flame seems to be alone again, and the glow disappears into the dark. Before we leave, hold two hard facts close. The paradox has been durable over hours and repeated nights, and perihelion sits close on the calendar, the kind of heat that redraws electrical sheaths and cracks stubborn crusts. Both facts argue for patience. They also argue for decisive tests. The open question is gentle but pointed. If the veil is self-made plasma, will stronger sunlight collapse it and let dust spill, brightening the optical wings at last? If it is an engine of vents, will non-gravitational drift spike as activity peaks? If it is a cloak, will the design fail gracefully under stress, or hold its shape until the traveler swings away? The possibilities are bold, but they do not demand miracles to be tested. The sun will turn up the gain in a handful of days. Heat, torque, and wind will force the system to choose its lines. The next section is the natural experiment, where perihelion becomes less a date and more a furnace that grades every story we have told so far. Five days fold into one bright edge. The sun gathers its heat like a lens, and the visitor glides toward a furnace that does not argue. Whatever hides in cold shadow will have to speak in light. Near perihelion, the rules simplify. Energy rises. Stresses add. Subtle habits that held for months can fail in a single afternoon. If the paradox of bead and lantern is a matter of inventory and vents, the furnace will tug at both. A compact core must either keep its outline under sharper illumination or concede a faint veil. A molecule-rich mantle must either thicken with new species or show the limit of what narrow seams can feed. Hold a clean image. A dark bead rolls down a warm pane and meets a band of sunlight. The band is only a few centimeters wide. Inside it, the bead sweats and glows. Outside it, the bead is quiet again. Our traveler is about to cross that band. Two hard facts anchor the next hours. Perihelion falls on October 29th, the point on the track where solar input peaks for this passage. Typical sublimation thresholds tell us carbon dioxide will already be lively by then, while water, if it has not yet joined in force, will be tempted to do so as temperatures climb by tens of degrees over recent weeks. These are not guesses about personalities. They are ordinary responses of common ices to sunlight. Cluster the compact numbers before letting them go. Gas speeds near a few hundred meters per second in the current regime. Rotational periods likely near hours. Mechanical strengths for centered crusts in the tens of pascals. A TESS scale of tens of thousands of kilometers per pixel for broad stacks. Each figure is round. Each sets a threshold that warmer light can push across. If the core is truly compact and the coma genuinely dust poor, visible profiles may remain tight even as the infrared grows another step. That outcome would favor the stage transformation story. Carbon dioxide would keep its lead. Water would add a quieter line. The optical band would still lack glitter because the grain size distribution and cohesion have not yet shifted. There is a second path. Heat widens vents and weakens seams. A flake lifts clean away. Fresh material with softer cohesion meets sunlight. Under that condition, grain lifting crosses a threshold and a thin dust veil forms. The visible point acquires shoulders, not a dramatic skirt, but a measurable fattening of the wings. In the infrared, water lines rise beside the old notes, and the ratio tilts toward a gentler split. The paradox softens because both senses begin to share more of their story. A third path leans toward failure. Spin up under sublimation torque quickens. Slopes fail. Blocks tumble from a rim and expose a bright patch that has slept for ages. The surface flashes and then dims as the patch crusts. The flash is brief, the dimming slow. A waveform like that in brightness would test the patience of a pipeline and reward high-cadence watchers. The visible profile might widen briefly. The infrared might surge and then settle. All of it would still live within a single body that keeps its identity. Imagine the traveler as a walnut again, this time placed near a flame. The shell creaks. A seam opens a fraction more, not enough to shatter, enough to let a longer ribbon of steam escape. To the naked eye, the nut still looks like a small glossy dot. To the right sensor, the dome inflates. If the seam snaps, a flake departs. The dot changes. The dome changes. The difference between a breath and a fracture is not magical. It is load and time. Two more facts keep us honest at the edge of suspense. Non-gravitational accelerations from asymmetric outgassing can nudge the track by measurable amounts across days. And rotation is mercilessly practical. A vent that faces dawn will wake each local morning and rest each local night with a gentle lag. If a veil forms, it should not appear as a single sudden wall. It should appear as a soft, repeating rhythm that builds toward perihelion, then wanes. Grounded speculation belongs here, modest and sharp. If a thin plasma sheath has been discouraging the mid-sized glitter near the core, stronger sunlight and higher gas densities may collapse or rearrange that sheath. When that barrier falters, fine grains can couple more strongly to the flow and escape. The visible band then receives back its missing sparkle, though perhaps only in a narrow collar just outside the point. A delicate widening would confirm a physical change rather than an optical trick. This is the natural experiment the calendar has written. No special maneuvering, no privileged instrument, simply hours of sunlight at a new level, repeated across a spinning surface. The test is not one measurement. It is several lines of evidence that should agree if our models have the right knobs. Visible wings, infrared ratios, astrometric drifts, polarization whispers, and any brief flashes in light curves form a small choir. If they rise together, even gently, we will know which path we are on. Hold another image to steady the breath. A lighthouse beam crosses fog at dusk. For many minutes, the fog seems thin. Then the air cools another notch, and the beam paints a faint wall out to sea. The wall was always possible. The temperature moved a dial. The lamp never changed. Only the medium chose a louder voice. There is a temptation to treat perihelion as a verdict. Survive and the story is one thing. Break and it is another. A calmer reading says the core question is not life or death of a small body. The question is whether the two registers we have been listening to decide to share their notes. If bead and lantern converge even slightly, we learn how vents widen and how dust joins the dance. If they do not, we learn how stubborn a sintered crust can be under stress, and how easily a molecule-rich atmosphere can stay shy. Set down a compact observing plan in words rather than numbers. Deep visible imaging before, during, and after closest approach to track any growth of shoulders. Simultaneous infrared spectroscopy to watch the carbon dioxide and water lines trade weight. Careful centroid tracking to catch small thrusts that speak of organized vents. Polarimetry to taste for new dust. Each element is routine. Together they turn the furnace into a lab. A final gentle question closes the loop without drama. When light pushes hardest and the nucleus rolls through its hottest noon, will the scene show us more of the same two voices? Or will the edge conditions invite a third voice that changes the harmony? Not catastrophe, not miracle, only a change of key that teaches what this body has been hiding. At the furnace edge, 4 paths divide. Break apart, brighten, go quiet, or glide on. Each path writes a different signature across light, position, color, and time. If fragmentation arrives, it will not be a mythic shattering, more a quiet unzipping. A stressed ridge yields, a plate lifts, then separates into a companion that drifts a little behind. In visible images, the photocenter begins to wobble, not wildly, just enough that a careful fit prefers 2 points rather than 1. In deep stacks, the once perfect profile grows a shoulder that refuses to fold back into a single symmetric curve. The light curve learns a new beat, small brightenings when the pieces expose fresh interior, then softening as frost crusts again. 2 hard facts will steady any such claim. First, fragments in close company shift the combined center of light in patterns that repeat with rotation and viewing geometry, an effect small but measurable across hours. Second, fragments with fresh surfaces often show short-lived color changes and an increase in polarization because new grains are released before the crust can rebuild. These facts do not require exotic models. They are the ordinary optics of pieces learning to share one orbit. A vivid picture brings the nerves down. Think of a thin lake skin that cracks under noon sun. 2 flows drift apart by a few meters, and the join grows a bright, fresh line. From a distance, the lake is still smooth. Close up, the line is honest. It shines and then dulls as the air chills. Cluster the compact technicals, then let them fade. A separation of a fraction of an arsecond at typical observing distances can betray a companion. Brightening by a few percent is enough to announce exposed frost. Polarization changes of a few tenths of a percent tell on fresh grains. None of these numbers must be sharp. They mark scales that trained observers can reach. If brightening rather than splitting is the headline, the signs differ. The optical profile stays almost point-like, yet gains soft shoulders. A delicate thickening that was absent before. Narrowband filters begin to catch shallow bands from familiar radicals. In the infrared, water lines lift beside the old carbon dioxide notes. Ratios slide from their earlier extremes toward gentler splits. The nucleus has not failed. It has learned a new habit. Vents widened, or a small slide refreshed a patch. The lantern and the bead begin to agree without fanfare. Here 2 hard facts recur, modest and useful. As vents widen, grains near the middle of the size distribution are the most easily lofted, which increases visible scattering far more than thermal emission. And when water joins the outgassing in earnest, day-night modulation grows because water responds strongly to the local morning and afternoon. If monitors see a slow rise of those mid-sized grains, and a daily breathing in the water lines. Brightening wins its case. Quenching looks different. It is a hush, not a collapse. Gas lines decline together. The infrared melody softens by simple ratios, without a new instrument taking the solo. The optical profile remains a tidy point, perhaps even a touch sharper as the faintest shoulder recedes into noise. Non-gravitational drift calms. The calendar offers two natural reasons. Either the accessible pockets have been spent for now, or the crust has annealed into something harder and less generous. The play is not over. The stage lighting turned low. A grounded speculation belongs here. If a thin plasma sheath near the core has helped keep mid-sized grains from forming a bright collar, then an increase in density near perihelion may rearrange that sheath. If the sheath collapses because recombination outpaces ionization locally, grains couple more directly to the flow, and a faint veil might appear. If instead the sheath stabilizes as flow smooths, the collar stays thin and the visible point holds. In both cases, plasma acts as an invisible set of rails, not a magician, and either outcome leaves fingerprints in polarization and in low-frequency radio behavior. Steady flight is the quietest branch and the hardest on human impatience. The optical profile stays star-like. The infrared remains a robust lantern with carbon dioxide still leading, water joining only modestly. The light curve shows nothing but rotation scale undulations. Centroid drifts match small, steady, non-gravitational forces that have been present all along. This path is not the absence of physics. It is a vote for a stubborn crust, narrow vents, and a chemistry that prefers gas over glitter even at higher heat. It extends the same story rather than flipping the page. Hold a single careful image. A kiln warms a sealed pot. Hairlines appear. None of them run. Steam whispers from the thinnest lines and curls along the rim. The pot shines no brighter to the eye, yet the air around it is clearly warmer if you place your palm near. The object survives with dignity, and its breath remains the main event. Across all branches, the map of signatures is simple enough to memorize. Fragmentation gives you a photocenter that refuses to sit still, a small new companion in fine seeing, a rise in polarization, and often a brief color shift toward fresher dust. Brightening without splitting gives you shoulders on the visible profile, narrowband hints of common radicals, a tilt of the infrared ratio toward more water, and perhaps a gentle daily pulse. Quenching gives you a synchronous fading of several lines in the infrared, a cleaner optical point, and a reduction in any tiny thrusts. Steady flight insists on patience. The same bead, the same lantern, with only the smallest seasonal edits as the object rounds its hot noon. Gather one more compact breath of numbers and let them go. Rotations in hours, not minutes. Thermal skin depths in centimeters that smooth sudden shocks. Typical non-gravitational accelerations, small enough to shift a path by tiny fractions of an arcsecond across a few days. Polarization changes by tenths of a percent that still speak loudly to the right instruments. FR, the dust proxy many comet watchers use. Rising by only tens of percent can mean the veil has arrived. These are the scales of change to expect. Small, cumulative, persuasive. What should a calm watcher listen for in real time? First, the shape of the point, measured against the instrument's own fingerprint. If wings appear, even shy ones, write it down. Second, the relative weight of the infrared lines, especially whether water takes a fair share. Third, the path on the sky, precise positions that can reveal any change in thrust as vents evolve. Fourth, the polarization, small numbers that often tell you the most about grain inventories. Fifth, any brief flashes on the light curve that last minutes rather than hours. The calling card of a small slide or a plate that suddenly lifted. The gentle question that remains is not a cliff. It is a room with 4 doors. Which door teaches us the most? If fragmentation occurs, we get a laboratory of fresh surfaces and a chance to see how quickly crusts rebuild. If brightening without splitting wins, we learn where the thresholds for dust lifting truly sit. If quenching arrives, we learn how stubborn sintered skins can be, and how quickly a carbon dioxide-rich coma can ebb. If steady flight prevails, we may have met a traveler that tells us interstellar inventories can produce a season of gas with very little glitter, even at high heat. And with the image that lets the shoulders drop. Night air over a quiet bay holds a thin mist. A boat passes near the channel marker. The marker's lamp stays a clean dot, steady and small. The mist glows a little in that light, then fades again. Whether the boat brushes the fog into new shapes or leaves it alone, the lamp keeps its pulse and the water keeps its hush. Observation is a kind of listening. In the next hours, the sky will decide which song to play. The quiet test nears its last page. Instruments keep their vigil. What follows is not a verdict, but a translation, turning 2 clear voices into one patient, measurable story we can sleep beside. The puzzle is now a map. One view keeps its tidy point, measured against the instrument's own fingerprint night after night. Another registers a wide, molecule-rich lantern that hums in the infrared. Each view has been steady for hours at a time, which means neither is a trick of a brief flare or a lucky angle. They are habits. Habits survive heat if the materials and pathways that feed them persist. Hold a simple image. Breath on a winter window softens the glass into a pale cloud. A lamp across the street stays a clean dot through that haze. If you change your eyes, the haze becomes the whole picture. Neither eye lies. Together, they draw a deeper room. 2 facts sit in the center and do not move. Perihelion falls on October 29th, when sunlight will push temperature and stress toward their seasonal peaks. Deep, visible stacks still match a stable point spread function without growing honest wings. Against those anchors, the rest of the story arranges itself calmly. Gather the compact numbers in one breath. A pixel footprint near 50,000 kilometers at these distances. Gas speeds near a few hundred meters per second. Rotation measured in hours. Carbon dioxide outweighing water by roughly 8-to-1 so far. Non-gravitational nudges small but real when vents are narrow. Each number is round and enough. If faint shoulders appear around the point, the dust lifting threshold has been crossed, and water has likely joined the outgassing with new confidence. If the point stays crisp and the infrared grows only a little, a dual state persists, with tight vents feeding a gas-rich envelope and grain production still suppressed by crust, chemistry, or charge. A slight astrometric drift would favor organized vents that act like an engine. A gentle rise in polarization would argue for fresh grains. A low murmur in radio bands would point to a changing plasma sheath close to the nucleus. None of these outcomes requires drama. All of them belong to one object trying on heat. Let the image slow again. A lantern under thin silk will look like a solitary bead if you stand far away under noon sun. At twilight, the silk reveals its dome. Walk back into daylight and the dome fades. The lantern has not lied. Daylight has a taste it prefers. The open question is modest and sharp. When the sun presses hardest and rotation brings each seam through its brief noon, will bead and lantern choose to share more of their lines? Or will they keep their distance and teach us that cores and coma can decouple longer than we thought? Either answer is a gentler taxonomy, not a cliff. All that remains is to listen without hurry. If the point grows shoulders, we learn thresholds. If it does not, we learn how stubborn certain crusts and chemistries can be. In both cases, the lesson is the same shape. Patience turns paradox into language, and language into rest. Set the charts aside. Let the calendar tip quietly into tomorrow. Picture the traveler as a small, dark kernel, threaded by seams, drifting through a field of light that arrives one photon at a time. The sun does not shout. It speaks in warmth, syllable after syllable, as if reading a patient story to a child. From one window, the object is only a pin of brightness, a polite point that neither grows nor frays. From another window, it is a hushed globe of breath, a soft lantern drawn in lines too quiet for the eye. Two windows, one house, two senses, one visitor. You do not need to decide between them to feel their harmony. Breathe in and gather the round numbers like smooth stones in a pocket. Hours for rotation, tens of thousands of kilometers for a pixel's reach, a few hundred meters per second for the pace of gas, a late October date for the moment of closest light. Stones are reassuring because they fit the hand. Let them become light and fall away. Imagine standing at a cold pane before dawn. Your breath writes a cloud that fades, then returns. Across the street, a porch lamp holds still. Nothing is urgent. The street will carry on whether or not the glass fogs. The same is true above you. Heat will loosen a seam. A seam will whisper. Some grains will join. Some will wait. The story will unfold at the speed of small things. Whatever this object chooses in the bright hours ahead, it is not a threat, not a secret hinge on the world. It is a lesson in attention. It shows how two honest instruments can disagree and both be right. How matter can carry more than one face without contradiction. How listening with two ears is not confusion, but depth. Let the last questions drift out with the tide. If a faint veil appears, you will know why. If it does not, you will know a different why. Either way, the sky remains kind, and the work of the night is simply to rest, while light and stone continue their quiet conversation far from shore. Close your eyes. Let the bead hold its shape and the lantern keep its hush. The cosmos is very large and very patient. Tonight, it makes room for you to be both.